So, good morning. Today is Thursday, September 28th, I think, right? But for all intents and purposes, let's pretend that today is Tuesday, September 26th. Okay? And we're going to end daylight savings time, so to speak, early, and we're going to rewind the clock one day in this class and go backwards and redo the what should have been last class, okay, in terms of the material and everything. And it's going to mean some changes to the schedule here. I'll redo this in a minute, but my ponderings last night on things were that you're in no way, shape, or form ready for an exam next Tuesday. And, you know, believe it or not, professors are not evil, horrible people. All right? My goal is to have you learn. But at the same time, in my defense, it's not all just what I want and me. You know, I'm trying to think of some new snappy slogan things for chemistry, for example. And for YCP chemistry, you know, one of them is take the risk and get the reward. All right? But what does that mean? The risk means, honestly, setting aside some of your personal life. You have to risk, I think, giving up some of your personal life. Unfortunately, you guys are in a very different place in the world nowadays than where I was when I was 20, 21 years old. Okay, there weren't as many other distractions for somebody like me or a Dr. Foy or, you know, Dr. Halligan, right? And so it was actually a little easier for us to concentrate on our studies, and there weren't as many distractions. So that puts a little more responsibility, I can acknowledge, on you as the student to say, well, yeah, I do have to suck it up for a couple years and have less now so that I can have more later. All right? And it's super hard to do that. But on my side, so I realize you're not ready this time. I can't push the whole semester back, right? I mean, I can't push your final to Christmas Day, for example, if we looked at the bottom, right? So at some point, you have to get up to speed with what your professors are doing, or then you will face the real consequences of failing, all right? But this first time, I think I've looked at the syllabus. We're going to be okay. I'll make some minor adjustments. But in the immediate near future, we'll move our practice day to next Tuesday, the 3rd, and our first exam to the 5th, and then I'll revise what's going to happen for the rest of the semester here and share that out with you. But you don't need to worry about the rest of that right now. You just need to worry about the next week for this course for right now. Okay? So that's number one. Okay? So hang on to the homework that you have right now in front of you, because you may want to make changes to it after you revisit the topics that we do in class today. All right? So I hope you didn't write in too much pen. Or if you need a clean copy of it to start all over, I can manage that as well. I get free copies. So, you know, if you need extra copies, I can do that for you too. All right? So that's that. All right? Now, the homework that I handed back to you, let's look at that one, because I know there were some questions, and I didn't grade the front part of it, because, I mean, all these ones and ones and ones, it's like, what is that? Like 1, 2, 3, 4, 5, 6, 7, 8, 9 little things per each thing times. It was going to drive me insane. All right. To grade these. All right, so I started and realized it was a lost cause. So let's look at this, and I think this will help us with what we're getting into with these total reducible representations as well. Okay, so again, your front side wasn't graded on homework 4.3 that I just handed back to you, but now you can. And I'll post this later on, so you'll be, you know, if you don't get it right now, you'll be able to make your corrections later. So what the instructions asked you to do were to, and I wanted to use non-molecules for the most part here. I wanted to have you, does that work actually? Oh, it does. Okay, good. All right. I wanted to use non-molecules and just other shapes and have you think about how they transform. And I picked this D2H group when I made this exercise a year or two ago because it's got lots of operations, so you get lots of practice with it. And it's frustrating if you don't quite grasp what you're doing, right? But anyway, so if we took the H, the letter H, in other words, and we performed the E operation on the letter H as it sat on this coordinate axis, how would it look afterwards? It would look exactly the same. And so that would be a positive 1. It would be symmetric, so it would be a positive 1, right? And all these operations, no matter what we do to the H, it is completely symmetric in all ways, all right, that we could operate on it. If we rotated it around the z-axis, right? If we rotated it around either the x or the y-axis, it always is still going to look like the H, right? In every single one of these, even the inversion, right? Because it would invert like that. So that's why H has all 1s. Now, when you have all 1s, and we want to assign that representation, right? So gamma's generic, right, for an irreducible representation. So we talked about how those labels are assigned. The first letter of the label depends on the character of the E operation. These characters can always be only 1, 2, or 3. All right? If it's 1, then we have 2 possible labels for it. If it's 2, the label is E. If it's 3, the label is T. As easy as that. But if it's 1, then you have to go to the next level, which is to look at a C2, or the principal axis of rotation, whatever the highest axis of rotation is, which is a C2 in this case. If that value is 1, it would be an A. If that value is -1, it would be a B label. Okay, so in this case it's 1, so that's where the A comes from. All right. And then if there is a, and I guess it's kind of tricky here, maybe this should be A1G now that I rethink this, because if there are perpendicular axes, then that's where the subscript 1 or 2 comes in. All right? And there are technically perpendicular C2 axes here, so I think really I should redo that and consider that to be an A1G label. So the 1 would come from the secondary C2s, the perpendicular C2s. The G is a label that is assigned when your group has a center of inversion in it. And so this does. The D2H group has a center of inversion, and so we would consider whether the operation is symmetric or antisymmetric, or whether the object is symmetric or antisymmetric after the operation. Positive 1 means symmetric. That is G, the Garrod label then. Okay? So now we have a sort of a flag. All right? That's what this is supposed to be, like a flag that's just split in half, 2 colors, one on top and one on the bottom. Okay? If we perform the E operation, the flag looks identical. Right? If we perform C2Z, where the Z-axis is supposed to be this vertical one here, okay, the molecule looks the same, all right, because we would just flip it around that way, and so it would still be blue on the top, black on the bottom. So that's where the +1 comes from. If we perform the C2Y, all right, which is the one coming out of the board, if we rotate this 180 degrees like that, the blue is going to end up on the bottom, and the black is going to end up on the top. You see that? Okay. You know, my object here, it's going to rotate just like that, and in this case, what you see on the right side as you're looking at it is now on the left side. That's the C2Y axis there. Okay, got it? All right. All right, so that's where -1 comes from. The C2X axis would also be, if we took this and spun it this way, again, then the top would flip down to the bottom. And so that's where the -1 comes from. Center of inversion would be that point right there, right? So this upper blue corner in the right would flip down here to the bottom left. So blue would go to where black is, black would go to where blue is. Again, that would be anti-symmetric, so it's -1. Okay, all right. Sigma xy. So the xy plane is, you have to think about what your x and y axes were. This is our y-axis, this is our x-axis. So the xy plane is a flat plane coming out of the board. If we reflect through that, again, we're going to be flipping blue and black sides of this. And so we're going to get -1. But the xz plane, which is xz, is a vertical plane like this. It's going to keep blue on the top and black on the bottom. So it's +1. And then the yz is going to flip the left and right sides, but blue is still going to end up on blue, black on black, so it's going to stay symmetric. All right, so those are the ones there. Okay, so that's how we get all of these characters here.
Did you want us to use the coordinate that you have in the top corner?
That's what I wanted, but I'm thinking, is it this?
It's y in the vertical position.
Z. Okay. All right. Z is coming out. All right. That I think it was supposed to be Z going down or whatever. Does that change some of these values then? Yeah. Well, forget that then. Then this is Z. What my answer is based on is Z coming out of here. So okay.
Do you want us to just have Z in the vertical?
Well, yes. The usually what we do, Z ultimately is the CN axis. Whatever the molecule's CN, so if it's a C3, a C6, that becomes the Z. But what we tend to visually do in our brains is orient that as being vertical, all right, to establish then what X and Y are, all right. So, yeah, so Z should be vertical there. Okay? So now, this is a unique set of characters, all right, that describe a symmetry in this D2H point group. 1, so this is an A or a B. +1 with, again, with redefining Z as the vertical axis, so we know it's A then. But -1 for one of the perpendicular C2s. So the subscript is 2 now, as opposed to being it should be a 2. I don't know why I put a 1. Again, I got this. I think I must have changed my axes and then I didn't change my labels there. Okay, so this should be a 2 because it is anti-symmetric in rotation of a perpendicular C2. And then it's also anti-symmetric for inversion, and so that's the U instead of the G that we have up here. All right. So this is a Word document. So let me change these real quickly here while I'm thinking about this. I can actually, I don't know if I can change my picture right there, but this one I can change down to being a 1 G. And then this one, like I said, I think should be a 2U. Okay. Was there a question there, Josh?
So it's a B2U?
B2U. Oh, no, sorry. This should be an A2U. A2U. A2U, because it is symmetric on what we're calling the Z-axis here. Okay? All right. All right, so now if we continue these, let's just go through all these. So if we do this Dxy orbital, so here we have a different set of axes defined, all right? Right? We're looking down the Z-axis at this one, and so there's our XY plane, okay? So now if we do the E operation, obviously it's unchanged. That's, pretty, you see that a lot, right? So pretty standard. So now if we rotate on the Z, the blue rotating 180 degrees will end up where the blue is. The white part would end up where the white part is. Right? So it's going to be symmetric. If you rotate around the Y, though, the blue half is going to get rotated and end up this way. So the colors would switch, the colorations would switch, which is the signs of the orbitals being positive, where it's positive or negative, the wave function. All right? So that's negative. Same thing for the X. It's going to flip the top and the bottom. For I, it's going to be symmetric, blue to blue, white to white. All right? And then for your XY, which is the plane of the board, so it's actually in the plane, it's flat, it's not going to change anything, so it's symmetric. But for XZ coming out of the board, all right, along that X-axis, the blue on top would flip down to the bottom, the blue on the bottom would flip up to the top. All right, so we'd have a top-to-bottom switching like we had with the flag in the previous example. So that's why it's negative. And then for the YZ, again, coming out along the Y-axis towards us on the Z, now we're going to be reflecting across that. So we're going to have left-right switching. So again, the blue to switch with the white switching with the blue. So it's negative there. Okay? All right. I think I have the wrong label here again. All right, because the principal axis, if we're calling the C2Z the principal, it's symmetric, so this should be an A, and then it should be a 2 because of the -1 for a perpendicular, but it should be a G. Is there a question, Patrick?
I just want to make sure I understand, like from classes too. So if there's no law on this for diagonal planes of projection, there are some in this, right? Because if you ran one through both of the blues, for instance, it would reflect the white of the cell and half of the blue into the other half.
Oh, okay, so a dihedral mirror plane, yes. This particular object possesses that, all right? But that is not necessarily something that that every object has, I guess. Okay, yeah. All right. So change that to A2G. I think I'm going to have to change this one to A1G. So this dx squared z x squared z y squared, sorry, is just like our h that we started with, right? Every way we flip and change this thing around, it's going to look exactly the same. And so it's completely symmetric. And so because of our perpendicular axes, we added the 1 into that. So that should be an A1G label there. All right. And then our last one, oops, somehow it's cut off. Looking like it's cut off when I do that. I don't know why the page.
Probably because you have lines in between.
There we go. Okay. All right. So there's our last one here, hexagonal sort of thing. All right. So we come up with something a little bit different here. We, again, are symmetric for E. For our z-axis, all right, if our z-axis is back to what earlier we said it being vertical, all right, this might change some of these, but that's going to actually be symmetric, right? These two are going to rotate around and end up on each other, and the two white sections at the bottom will end up on each other, all right? Rotation around the y-axis coming out of the board is our y now, is going to bring this down to here, all right? It's going to swing it 180 degrees, so we're going to see changing of the colorations, all right? So that's why it's going to be negative. Same thing for the x. The x-axis coming through would flip the top and the bottom, so it'd be -1. Inversion would swap colors since everything is opposite a color, or, you know, on the opposite sides, a different color. The xy plane, that's this one coming out of the board, so that should be -1 because the top and the bottom would switch. The xz plane, all right, would be a switching of the left and the right, sorry, xz is the flat, xz is the flat of the board actually, so this is a flat object, so it's you know, right on itself. In other words, the top and the bottoms are on itself, so it's symmetric. And the YZ is the one coming out of the board like this. Left and right are going to switch, but they are symmetric as well. Right? So we've again got, I think this should be an A. I don't know how I got B's in this group here, but yeah, you know, if we're calling C2Z the principal rotation axis, then this should be an A label. It should be a 2, all right, and it should be a U, so it should be an A2U. So the previous one should be A1G, and this one should be an A2U. All right. Okay. So that's the main part I wanted to go over with that. Most folks did pretty well on the back part on these reductions, all right? But for now, we'll leave that as it is, okay? All right. Let's look at some of the topics then that we were looking at last class. The concepts of developing then these total reducible representations for a molecule. All right. So I handed out this handout last class, and we went through the water molecule. Let's look at the back side and just see if we can't confirm the XEF4 part. All right. We kind of ran out of time to consider. All right. So XEF4 is a planar molecule, and often gets drawn this way, right, using the three-dimensionality, because there's a lone pair of electrons above and below. Okay. That is the C4 axis that this molecule contains, is vertically, and that's going to also define then our Z orientation. All right. Then your x-axis should be determined to go through as many atoms as possible. It wouldn't really matter, but it's going to go through one of these, okay? And then that's going to mean the y-axis actually comes through the other one. Right? So you need to establish for yourself the x, y, and z directions. Z, again, should be coincident with the highest Cn axis that you have in your molecule. X should try to get as many atoms of the molecule in the same plane, the xz plane, all right? And then y is defaulted into what's left over, all right? That's sort of the general way to do it. But here, x and y are really the same. They're going to be degenerate, okay? So this is part of the D4H point group. Right, which has several operations. E says 2C4, it says C2, 2C2 prime, so that means they are a perpendicular to C2 double prime. Another, that's going to be a diagonal, actually we'll see, or dihedral sort of. 2S4, sigma H, 2 sigma V's, and 2 sigma D's. So let's attempt to visualize these, all right, and figure out how what the total reducible representation is. Okay. Now here's something that I ran out of time last class to distinguish between. When we do the total reducible representation, you are considering all atoms, x, y, and z coordinate vectors. Right? So you're doing what we did last class with your z, your x, and your y, your fingers. Okay? Now after we do this, I'll distinguish that against two things that you were asked to do in your homework. For the carbon monoxide stretches, or for the particular bonds in number 2, the carbon-chlorine bonds, we don't have to consider the whole molecule. All right? So there's a time and a place when, if we know that a certain piece of a molecule is what's going to provide the signature difference, right? We're trying to figure out if something is cis or trans, okay? We don't have to look at the whole molecule. We just have to look at that particular bond and how it's going to behave. And that's what question 2 on your homework was supposed to hint at, okay? So we'll go through all that, all right? But for XEF4, we have a total of 5 atoms, right? So each of these 5 atoms, that's our N value, has 3 coordinates in it. So if all of these remain the same under the identity operation, 5 times 3 is 15. Okay? Now, we have next our C4 axis, which we've already identified. Okay? The number 2 out in front simply means that there are 2 C2 axes, 2 C4 axes, actually. The other one is coincident with this one. It's just if you choose to look at the molecule going in that direction. And that sounds cheap, and it is, okay? But if you look at the molecule from the bottom up, it switches what X and Y are, and so it's technically a different axis of rotation, all right? So for the purpose of developing what we're doing here, though, it doesn't affect it at all, okay? The only thing that affects is the order of the group, remember, which is the sum of all of these coefficients up here, okay? So maybe we'll do that if we do a reduction, but I don't, this is a huge one, so I don't think we would reduce this, okay? So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 is the order of the group, okay? All right. So that's really the only thing that it affects. And then when you're doing the reducings, you have to take into account those coefficients as part of the reduction formula. All right. So when we perform a C4, right, if I labeled my fluorines 1, 2, 3, and 4, and I rotate this thing 90 degrees, 1 ends up where 2 is, 2 is where 3 is, 3 is where 4 is, 4 is where 1 is, right? So any atom that physically moves, none of its coordinate vector is still here, right? So you have to imagine a little ghost image of my hand, right? Now, as I rotate 90 degrees, none of that is still right there. So this fluorine atom, you could think of my hand right now being this fluorine atom, none of its coordinates are in any way connected to where they were before. So it contributes nothing to the total reducible representation of this molecule. The only atom that doesn't move is the xenon atom, okay, in this case. So it's the only one that possibly contributes. So now on a C4, if we draw it one time here, we can't do this every single time. So if this is our Z, this is our X, and this is our Y, if we rotate this 90 degrees, our Z is still there, our X is now back there, and our Y is here. So Z is the same. So that's a +1. Y has become what X was. So that's a 0, actually. In other words, none of the Y vector that originally is pointing out towards you here, think of it right now as 100% or 1. What amount of it is still pointing in that direction when it rotates 90 degrees? None of it, right? All right, so that's why it's 0. The same thing for X. X was originally pointing here. Now it's pointing back this way. No amount of it is still pointing in its original direction. So its contribution is 0 since X became what was Y. Okay? So that's a 0. So the sum of those 3 things is a +1. So any C4 atom is always going to be a +1 per atom. There's only one atom, though, that stayed unmoved in the C4 operation. Okay? So it's really important, right? You identify how many atoms don't move upon doing this operation. Then, separately, you figure out, for the operation, what's the contribution per atom. Then you bring those 2 things together. How many atoms, contribution per atom, that gives you this right here. Okay? All right. So our C2, all right, our main C2 is, I believe in this case, going to be coincident with the C4. The C4 is also a C2 axis here, right? We could rotate along it, okay, by 180 degrees. So the only atom that's not moving is once again the xenon in that case, right? On a C2, we saw this last class, right? Our Y and our X, when we rotate 180 degrees, are now pointing completely in the opposite direction. So what percentage of Y is pointing in that direction? Negative 100%, or negative 1, right? What percentage of X? Now negative 100%, so negative 1. But Z was unchanged, right? So you have a negative 1 from Y, a negative 1 from X, and a positive 1 from Z. So that adds to negative 1. And again, there was only one atom, only the xenon experienced that, because the other things all moved. Okay? C2 perpendiculars. This is a C2 perpendicular going through, and there's two of them, right? The other one comes through here. Okay? That's a C2 perpendicular. So we see that it goes through 3 atoms. So now 3 atoms are experiencing this transformation and are going to contribute, right? But we don't need to reinvent this again. Every time an atom undergoes a C2, its contribution is negative 1. I have 3 atoms doing that, so this is negative 3. All right, this is the power of systematically thinking about what an operation does. It doesn't change from one thing to the next. These coordinates always behave the same way under C2. Okay? All right. Now the C2 double prime is sort of like a dihedral. It comes right through there, because we could rotate this, right? Because of the way they are, the front one and the back one can switch places. Or we could go right through the middle from the front, and the 2 in the front would switch places, and the 2 in the back would switch places. So now we're back to just one atom that doesn't move upon this operation. Again, it's a C2, so its coordinates undergo the same change that we had before, so we know that it's negative 1. Okay? All right. We stop there. Questions so far? We good with this so far? All right. Next, center of inversion. The xenon sits at the center of inversion, right? So it doesn't move. Everything else moves on the center upon inversion here. So only the xenon contributes. Now, what happens to all the coordinates? If we invert, Z that was pointing up now is pointing down. If this is your X pointing that way, it's now going to be pointing this way. And our Y, if it's back away from you, is now going to be pointing that. So it was this, is now this. Negative 1, negative 1, negative 1. Everything has gone in completely opposite direction, right? So the contribution is negative 3 for a single coordinate system. Now how many atoms are doing that? Only one. Only the xenon. All right, so it's negative 3. Okay? So I'm not writing it all out, but right, if you wanted to, what you could be writing out are underneath it, like which atom, right? Only the xenon, xenon, right, times negative 3. So you understand, or, this was actually 3 atoms times negative 1. So if you want to, really understand where all these numbers are coming from. All right, now what's an S4? S4 is an improper rotation reflection. So 2 things happen. The molecule is rotated according to the subscript 4, which means 90 degrees in this case, and then it's reflected. Right? So upon the rotation, everything moves except the xenon. Right? The fluorines all move just like they do in a C4. Okay? And then we reflect. So here's what happens to our coordinate system. First, it's rotated 90 degrees. So it's just like the C4. The Y becomes the X, so it contributes 0. The X becomes negative Y, so it contributes 0. The Z is still pointing up, though. Now we do the second part. We reflect. So it's going to point down, all right? And so again, these were already 0 contributions, but now it's pointing downward with a -1. So the net change is -1 for our 3 coordinates that we have there. Do you see it or not? Okay. All right. I'm not convinced that Courtney sees it.
I get it.
Get it? Okay. All right. All right. So it's -1, and only one atom underwent that had that coordinate system change. Okay. Sigma H, horizontal, the plane of the board, right? The sigma H is going to have 5 atoms then, because all 5 atoms are in the same plane. What's a sigma H do? It's going to take your coordinate system like this. It's the plane of the molecule, x, y. So the only thing that's going to move is the z, which is going to then point down. So +1 for x, +1 for y, -1 for z. The net change is +1 per 5 atoms. So we have a +5 as the contribution there. Okay. Your vertical mirror planes are going to be coincident with the C4 axis and 2 of the fluorines, either the x or the y axis. There's 2 of them, right? One along the x and one along the y. Right? So the vertical mirror planes have 3 atoms in them. Okay? Again, what's a mirror plane do? Doesn't matter if it's horizontal or vertical. A vertical mirror plane is going to take one coordinate and flip it across the other 2, the plane of the other 2. All right? And so it's going to take that and make it point that way. So again, +1 +2 -1. So you get a +1 per atom that undergoes that change. So that's going to be 3 for the vertical mirror plane. And then the dihedrals are along this C2 double prime, right? So it's like the plane of the board. So now the only atom that doesn't move is the xenon. Every other atom would move, all right, from front to back, back to front in this case, or left to right, right to left. So we're back to having only one atom, but yet again, it's going to be +1 per atom because of what a mirror plane does. It always is going to be flipping left to right, top to bottom, or front to back. 2 things are left alone. 1 thing is going to change. Okay? So this is now the total reducible representation of this molecule. All right? Okay, questions?
So anytime we have a C2 double prime, it's going to be rotating at a diagonal.
D we kind of think of as diagonal, yeah, but it's not along a line that contains multiple atoms of the molecule. It's usually between them, yeah. So it's in between it's in the middle of a bond. Okay, yeah. So sometimes they're tricky to find. Sometimes they're easier to see, like in this case here. Okay. Question.
So for the mirror plane, the last one, I'm just trying to make sure I have it right in my head. It would actually flip 2 of the axes and switch them with each other, right?
No, not really. Okay.
Does it come in like this?
So to the molecule it does, but not to then the coordinates. All right. So we can reestablish the coordinates once we are thinking about the actual operation itself. All right. Yeah. That sounds a little hinky to do that, but that's what you get to do. Okay. So so yeah, it's coming in like. If it's the flat plane of the board, okay, well, I mean, if you really want to, if it's the flat plane of the board, and if my thing is really oriented like this, because X and Y, all right, if we reflect it then, Z is unaffected, you're right, but then these two would go over in this opposite direction, okay? They're going to add to 0. The other way, mathematically, we would prove that it adds still. They still add to 0. So, okay. So we'd end up with, yeah, still a +1. All right. So it's really just easier to think. I think it's really easier to just reestablish my coordinates along the plane of the reflection itself. So, okay. All right. Other thoughts or questions on this? Okay. Now, what is this total reducible representation? It's describing how this molecule moves, transforms in space. All right? When its atoms wiggle and shake and move around. Okay? And it's got all the possible outcomes for, imagine you took a picture of the molecule, and then a femtosecond later you took another picture of the molecule, and its atoms had moved ever so slightly. That change is captured or described by essentially one of the irreducible representations of the molecule. All right? Within the 15 possible, things, 15 degrees of freedom, we know that 3 of them describe the molecule literally moving. If all the x-coordinates shifted together, or all the y's shifted together, all right, the molecule would move, we said. And then 3 describe rotation, the molecule spinning, all right, about an x, y, or z axis. So 15 minus those 6 means that there are 9 vibrations of this molecule. 9 ways that it can have its bonds stretch out or contract, bend, buckle slightly. Okay, we think of this as a flat molecule, but if one atom moves down and one atom moves up, what was a flat bond like this is now buckled, sort of like that. Okay, right. So all of those activities have a symmetry that they're associated with, which is captured and described by one of the irreducible representations of the molecule. And so the 9 that are left over, we can find what they are and find what their symmetries are. And then those labels tell us when we find that there's an A or we find that there's a B. A tells us that there's something the molecule does that is symmetric, all right, with respect to the C4 rotation, all right? Or there's something that might be anti-symmetric with respect to the C4. Okay? That is why we break down the total reducible representation into the irreducibles components. Okay? Now, sometimes we don't have to do the entire molecule. If there was a molecule that, I think on your homework the other day, it was missing, right? Is it the one that's on your homework? Where's the homework you had today? Homework that was due today. I had to tell you, yeah. So on the homework that was due today, you had this I, double bond O, and then the 4 or 5 F's, right? Like this, okay? We could examine just this molecule, or just this bond, all right? And we could see, how does this bond behave? So what's this part of? This is part of the C4V point group. So the gamma of the IO double bond, all right, the reducible representation for it So this is not what you're doing on your homework. On the homework, you're asked to do the total reducible representation, all right? But this bond is different than all the others, right? So it might be, I want to figure out, is this bond IR active? Okay, that's what I'd like to know. So I can tell if this bond is IR active, which would let me see it in an IR spectrum or a Raman spectrum, right? By developing a reducible representation for it. So what we're going to do is we're going to replace the bond with a vector that points from one atom to the other. Okay? And we're going to see how does the vector change with respect to each operation. This won't be very exciting since we have only one vector, all right? This would work a little bit better if we had two, all right? If we had two oxygens, okay? So indulge me for a second. Well, I don't want to change the point group. Yeah, it would change the point. I was going to put another one in, but it would change the point group and I have to start all over, okay? So, but I'll sort of try to demonstrate that to you. So when we perform E, the vector is, of course, unaffected, all right? When we perform a C4, the vector sits along the C4 axis of this molecule. So it's still going to be pointing exactly the same way it is. So it's 1, all right? When we perform a C2, this is also the C2 axis. The OIF is the C4 and the C2, so it's 1. When we perform a sigma V, all right, this is a vertical mirror plane that would include the 3 of the fluorines and the oxygen. That vector is, again, unaffected. And when we perform a dihedral, diagonal mirror plane through, between the fluorines, so the actual plane of the board, again, this is all unchanged. Okay? So we can tell that this is an A, all right, because it's symmetric there. This is not a perpendicular C2, so we can't look at that to give us the subscript. All right. This is then we default to the sigma V, symmetric, so it's 1. All right. So this is labeled A1. So now if we looked at the C4V point group, all right, which I don't think was given. No, the C4V was not given. So I'm going to look it up in the back of the book here real quick. So I find the C4V, all right? Yep, A1 is the label here. If I look out to the right, this has the letter Z next to it. And so if a reducible representation transforms, it describes the coordinates x, y, or z being transformed, we know that that mode is IR active. So this IO is IR active, and it should show up in an IR spectrum. Okay? So now if I was to do anything to this molecule, react it, right, that would try to possibly maybe break this double bond and have the oxygen bond onto something else, right? So it would no longer be, that. Okay? I have something that I can physically look at before and after to detect if a change has occurred to the molecule. All right? Another classic way we use this is if there was another double bond and we were wondering, well, is the second double bond down here on the opposite side, or is it in one of these positions right here? Well, our simple analysis, knowing about VSEPR and things wanting to get far apart, tells us that they probably would line up away from each other. Okay? But we could perform this analysis for the two double bonds being in opposite positions or being in adjacent positions. We would get two different representations. What we would then do is figure out, is there any IR or Raman activity that's different? So maybe, for example, one of them would show you 2 IR peaks and no Raman peaks. And the other arrangement would show you 1 IR peak and 1 Raman peak. That's a measurable difference then between those two structures. You get the molecule, you collect an IR and Raman spectrum of it, and you confirm which structure you have. If you see 2 IRs, that agrees with your theoretical prediction that the two bonds were opposite each other in that case. Right? You see how we use this as a way to help us understand how molecules behave, all right, and how they work with some of the instruments that you have used and that you'll learn to use a little bit more in your instrumental courses. All right. Okay. Now another thing on your homework was a molecule that had 4 chlorines, right? So it's 1122 tetrachloroethane, I think, is what it's called here. And I think you're supposed to look at it in this conformation, right? This conformation. Again, in reality, remember that a molecule like this carbon-carbon bond is loose, and it's able to spin. So this molecule only looks like this for a brief moment. And another moment later, because of everything being able to move, it's no longer like this. All right? Although this is probably the minimum, this is probably the best position because it gets those chlorines as far apart from each other. So we could go to the trouble of developing the total reducible representation for this molecule. There are, 8 atoms, so it would have like a gamma that starts out with 24, right? But what we're really interested in are these 4 bonds between the chlorines and the carbon. So you're really just going to develop your gamma for those 4 vectors, just like I did for the IO bond. So we can be selective, right? Because we're trying to figure out how these 4 things behave, if they're IR active, right? If they're the source in this conformation, if they're IR active or not. Okay? So you don't need a huge one for this. 4 is going to be your starting value, all right? And so then when you rotate this molecule 180 degrees, all right, that's tricky because when you rotate it, this vector ends up over here where another vector was, but it's like the coordinate system. It's not actually any way, shape, or form where it originally was. So because the atom moved, it makes no contribution. All right? So it's still the same idea. If an atom moves, its vector adds or contributes 0 to the reducible representation, to gamma. Okay? So these are all going to be like 4s or 0s. All right? There's no operation in this group that's going to allow these vectors to simply change direction. The only time you can get that happening where the vector might just change direction is going to be, that right, with some of the carbon monoxide ones that are on that homework set? No. So when we use this idea of these vectors, the values are always 0s or 1s. All right, and it's another simplifying thing. So another thing you had in your homework is this structure with carbon monoxides. I went through this at the tail end of class. Let's choose a slightly different one. Go through this analysis. There's one of these in the book. Yeah, so if we had a metal that had 2 ligands and then it had 2 carbon monoxides, those 2 carbon monoxides could be attached either trans, or the 2 carbon monoxides could be attached cis. Carbon monoxide is like a little spring, right? So it is, in addition to all the atoms moving around, the carbon monoxide itself is undergoing this, this degrees of freedom, all right? And so what we can do is we can look at vectors of the 2 carbon monoxide molecules pointing in towards it. Now these two molecules are in different point groups, though. They're not in the same point group, all right, because of their changes in their symmetry. So the first one, when they are trans, it's in the D2H point group, which is big, so I'm going to run out of room here, okay? The D2H point group has an E, a C2Z, a C2Y, a C2X, center of inversion, sigma XY, sigma Y, XZ, sigma YZ, okay? Yep, it's got all those. It's what was on the homework, actually, the first thing we went over in class, right? So these two vectors will both be in the same spots for the E operation. For the C2Z, which is going right down this molecule right here, okay, the Z-axis is coming out of the M, they're going to move. So the contribution is 0. For the C2Y, which would be the L to L, so this gets defined as the X-axis, right? And this gets defined as the Y, WHY. Why is that the case? Because X, you try to get as many of your atoms of interest into the axis, right? And so the carbon monoxides can be on the X. So the C2Y would flip the two carbon monoxides and have a 0. But the C2X is going to rotate the molecule along the X-axis, and these two vectors are the same, so they're each going to add 1. The center of inversion is going to move the two vectors, so it's 0. The XY plane, the board, is not going to affect the vectors, so it's going to be 2. The XZ plane, all right, that is XZ coming out of the board, is also not going to affect the vectors. They're still going to be right where they're at, all right? And then the YZ plane is going to flip where they're at, so it's going to be 0. Okay, so there's your total reducible representation, sorry. Your reducible representation for the two carbon monoxides. The other version of this is in the C2V point group, a much simpler point group. So the gamma for the carbon monoxide stretches here. There's E, there's C2, there's sigma V, and then there's sigma V prime, all right, which is YZ, and sigma V is XZ. So E is 2. The C2 axis is here. Here's your C2 axis, right? So the two vectors move. The sigma XZ, all right? So again, here's our Z, all right? And our XZ, but something's going to have to move, all right? So in this case, it's going to be 0 as well. Okay. Oop, no, I got that wrong. X is going to be the flat XZ. It's telling me that XZ is 2. Okay. How do they define their coordinates? Just looking at this real quickly. Okay, this is Z. They've defined this as X. So yes, the flat of the board, that's how they're getting 2. And then YZ is going to be 0 because it's coming out of the board. And so YZ is going to cause these two to switch. All right? Now, until we do the reducing of these, this would reduce without doing all of that. It shows us that this would reduce down to A1 plus B1. Right? So if we looked at the whole character table for C2V, which has A1, A2, B1, and B2, that's what this would reduce to. this one up here would reduce to AG plus B3U. Okay? It would take a long time to get to that, by the way, because there are lots of possible irreducible representations to test. Okay? All right. Anyway, if we now consult the right-hand side of the character table, for C2, A1 has the letter Z underneath it, or next to it, and it also has Z squared in the far right-hand column. B1 has the letter X in the column next to it, and the letter XZ in the far right-hand column. So in the cis conformation, there would be 2 IR bands and 2 Raman bands. Because each mode, each irreducible representation is IR active, and each one is Raman active. Okay. Now, if we go to the D2H point group, and we look next to AG, next to AG, there's nothing in the first column, and then it says Z squared in the far right column. And then next to B3U, there's an X in the first column and nothing in the very last column. So the trans conformation has only 1 IR band and 1 Raman active band. Patrick?
Just to clarify, the second, or the very last column is the Raman active?
Yes.
Okay.
Yes, the last column is telling you what's Raman active, what corresponds to the symmetries of the d orbitals. Okay? xz, xy, yz, x squared minus y squared, and z squared, or some linear combination of them, which is not, you don't see that too often. Okay?
For those values, like the z squared, the x, you just look those up once you have all the other information? Is there like a chart you look at, or?
Wait.
If you were asked to get those, how would you get those?
How would you get? They're in the character tables already.
Okay.
Yeah. So yeah, you would. There is a way to know what's x and what's y and what's z. It comes from the more sophisticated matrix math that we did earlier, knowing which representation was the x row, the y row, and the z row. That's ultimately where those come from. Okay. But now all the character tables are known. You could just look them up, and that's what you should do. Okay. All right. So this tells us a clear difference. So if we made this molecule, and we did the stoichiometry that put in 2 units of carbon monoxide, there's only 2 possible ways it could come out. Either the carbon monoxides ended up cis, or they ended up trans. How are we going to know which one we had? Right? Raman or IR spectroscopy is going to tell us the difference. You're going to take an IR, and if you see 2 big peaks, okay, they would be indicated, that would indicate this, versus two carbon monoxide stretches, right? So it's still a CO stretch that you'd look for in the IR spectrum, all right? Because there's tons of stuff that shows up in an IR spectrum, right? You'd see 2 CO stretches if you had the cis version. You'd see only 1 CO stretch in your IR if you had the trans version.
What happens if you get like a mixture? Then what happens?
Yeah, so then if you had a mixture, I don't know honestly. In your this is considering a pure sample, yeah. So if you had a mixture, you'd probably have to separate them. So okay. Another thing is they might be difference in polarities, right? There are other measurables that we can use, but in this context, this is identifying the spectroscopy differences that we can observe between molecules that's predicted by all of this point group stuff. Okay? All right. How are we doing? Other questions now? Can we go back to having the exam next week now on Tuesday now? No? Yes? No? Okay. All right. That doesn't interfere. I didn't ask Dr. Foy. That doesn't interfere with like a quant exam. No, that's not on Thursday anyway, right? So, or PChem exam or anything like that. I hate to move it and have it overlap with another. PChem doesn't have exams.
We just have quizzes.
Quizzes. Wow, Dr. Foy is mellow, or Forsman is mellowing. Wow. Okay. So, all right. So, okay. Very good. All right. So I think I've addressed everything that would now let you successfully or more successfully do your homework that you had, right? Okay. Okay. Sounds good. All right. So next class then, we are set up to review for our first exam then. Right. Our first exam is obviously all of this stuff, but it's also our covering of chapters 2 and chapters 3 as well. Okay. And I'll have a review sheet for you next class. All right. And we will, go over questions. So you should start your review. I had wanted to give you a second shot at quiz on chapter 4, all right, that we took last class, and I quickly realized was not worth the effort to grade, and folks did not do very well. So take this version of quiz 4. I added one additional question to it. It's the same as what it was the other day, but I added one additional question to it. And for your own purpose, take it. I'm not going to collect it. I'm not going to grade it. Okay, I'll post the solutions to it in a day or so. Okay, but I really think you should see if you get this stuff now after having another day to digest it and walk through some examples. Okay. Any better than you did before. All right? You need, again, your assignment, character or point group assignment chart for number 1. For number 2 here, that's this block diagonalization process. So each of these 3x3 vectors can get divided into 9 1x1 matrices. All right? And any non-zero values, okay, go. Well, actually, no, this can't quite be divided into, that's the trick to this one. It can't be divided into 9 1x1s. It gets divided into 1 2x2 matrix, and then the others are all 1x1s that are left over. See if you can figure out where the 2x2 is. All right? And so then you add up your diagonals to come up with the first two terms, first two irreducible representations that belong down here in the bottom row. And then the third one will be kind of obvious, I think. You'll see. All right. And then in the back, again, that one should be much more straightforward now. Again, orthogonal, remember, means that the product of two things is 0 when we take into account the coefficient of the operation. Okay. And then the two terms that we're multiplying to each other. All right. Actually, no, sorry. For orthogonality, we don't take into account the coefficient. We just straight up multiply the things together. All right. 1, 1, minus 1, 1, 2, 1, 2. We must take into account that. Okay. We must take into account coefficient. All right. And then you can see I added this last one, which is what we worked on today. All right. So, again, next class review. I will collect that last homework then of 4.4 that you're working on, but I'll give you a chance to go back and redo it. If you need a clean copy, you just want to start over, stop by and see me later today or right after class here. I'll print out some more, and we'll go from there. All right? Have a good rest of your day and a nice weekend, and we'll see you for a review next time.